We'll start by considering the rate of change of the longitude of the ascending node. Recall that Gauss's perturbation equations tell us that capital omega dot is given by f sub h times the orbital radius magnitude times sine of the argument of latitude divided by the magnitude of the specific angular momentum times the sine of the orbit's inclination. So all we need to do is plug in the third component of our perturbing force, as given here, into this expression, and we find that for J2 only, capital omega dot will be -3 times mu, which in this case is the gravitational constant times the mass of the major body, so for example, the mass of the Earth, times the major body's J2 coefficient, times its equatorial radius squared over the orbital radius cubed, times the specific angular momentum magnitude, cosine I sine squared of theta. We could now equivalently write down an expression for I dot using Gauss's perturbation equations, and recall that those equations also give us this constraint between theta dot and capital omega dot. So in theory, we could form a system of ordinary differential equations in omega, theta, and I, and we could numerically integrate those, and then we would see what J2 is doing to our orbit from second to second, but there's not really a lot of utility in that. Because remember, to do this, to write down this expression, we've thrown away the vast majority of the formalism that describes the true geopotential of the Earth. We're really just focusing on this one single dominating term. And so we can get an exact numerical integration of the system, but that doesn't describe exactly what is happening to our orbit because we're neglecting so many other aspects of the geopotential and also all of the other perturbing forces. Instead, the main point of doing this type of analysis is to see what these dominant effects, like the J2 effect, do to our orbit over the course of many orbital periods. And to do that kind of analysis, we really don't care what is happening from instant to instant along our orbit. And we only really care about what our orbit is going to be doing over the course of many periods, which means that we can just average these expressions over the course of one full orbit and then see what the long-term effects are. We start by writing d omega d theta is equal to d omega dt, otherwise known as capital omega dot, times dt d theta, or 1 over theta dot. We substitute in that previously mentioned constraint equation, and we find that d omega d theta is equal to omega dot divided by the quantity h over r squared minus omega dot cosine I. If we assume that omega dot is relatively small, then we can expand to first order in J2 as follows. We first rewrite this expression as r squared over h times capital omega dot times the quantity of 1 over 1 minus r squared omega dot over h cosine I. To this denominator, we apply the binomial theorem with the x value being equal to 1, the y value being equal to all the rest of it, and the exponent r being equal to -1. And expanding to first order in J2, we get d omega d theta is approximately equal to r squared over h times capital omega dot times the quantity 1 plus r squared over h omega dot cosine I plus all terms of order J2 squared, which is equivalent to saying terms of order omega dot squared, which we've said is going to be a small quantity, and so we're going to neglect these. We rewrite this expression. D omega d theta is approximately equal to -3 mu times the J2 term times the equatorial radius squared over h squared r times the cosine of the inclination times sine squared of the argument of latitude plus all of our higher order terms. And we will substitute for r using our conic section expressions. R is equal to the semi-parameter of the orbit divided by 1 plus e times the cosine of the true anomaly, which we can write as the difference between the argument of latitude and the argument of periapsis. We always have h squared over mu is equal to the semi-parameter, which for closed orbits is also the semi-major axis times 1 minus e squared. And so this expression here becomes d omega over d theta is approximately -3 J2 times the quantity r over L squared times cosine of the inclination times sine squared of theta times 1 plus e cosine of theta minus omega. Our reason for setting this up was that we wish to find the average of this variation over the course of one orbital period. In this system, theta, the argument of latitude, is the fast variable. It is the one that is nominally changing for a pure two-body orbit. And in the case of a perturbed orbit, it is still changing, we hope, much faster than all of the other things are changing. And so to get the average of the variation in capital omega, we need to integrate over the bounds of theta over one orbit, and then divide by the total change in theta over that orbit. That looks as follows. Over the course of one pure two-body orbit, the true anomaly goes from 0 to 2 pi. And so in the case where omega is a constant, theta also changes by a total of 2 pi over one orbital period. It doesn't really matter for our purposes where we start in this averaging, and so we can take our integral from 0 to 2 pi without any loss of generality. And this gives us the average value of d omega d theta, which evaluates to -3/2 J2 times the body's equatorial radius divided by the semi-parameter of the orbit, quantity squared, times cosine of the inclination of the orbit. This is the expression for what is known as nodal regression. Note that for inclinations below 90 degrees and above -90 degrees, this cosine will be strictly positive. For bodies with a strong equatorial bulge, like the Earth, J2 is positive. The equatorial radius and the same parameter of the orbit are both strictly positive quantities. And so in that case, for a prograde orbit, for an orbit where the orbital motion is in the same direction as the spin of the planet, this quantity will be strictly negative. And that means that the line of nodes will tack opposite the direction of the orbital motion and opposite the direction of the spin of the planet, hence nodal regression. For retrograde orbits, when you pass the 90-degree mark for inclination, the sign will flip and you will get the line of nodes moving in the opposite direction. The effect of moving the line of nodes is the same as clocking the specific angular momentum direction about the pole direction, about this E3 prime direction. I should note that in this figure, the effect has been exaggerated by a factor of 10 for clarity, just so we can more easily see what is happening. So this is in fact what the trace of the orbit would look like for a 30-degree inclination orbit at about 1,000 kilometers altitude, with a small eccentricity of 0.1 over 10 orbital periods, except that it's a factor of 10 larger. And so the change shown here for the longitude of the ascending node would actually be accomplished over 100 orbits rather than only 10 orbits. As previously stated, anything that we can do with Gauss's equations, we should also be able to do with Lagrange's planetary equations. So let's take a quick look at that. The Lagrange planetary equation for the rate of change of the longitude of the ascending node is given by this expression, which is a function of the partial derivative of the perturbing potential in I only. Our perturbing potential in this case, as previously stated, is negative J2 mu times the equatorial radius of the central body squared over the orbital radius cubed times 3 cosine squared phi minus 1 over 2, where phi is the zenith angle of the current orbital position. And we've previously shown that cosine phi can be written as sine I sine theta. And so we see that our perturbing potential is in fact a function of the inclination, meaning that we will get a non-zero partial derivative here. We evaluate the partial derivative, multiply everything out, and we get this expression, which exactly matches what we found with Gauss's equations. So we verified that we can in fact match what we achieved with Gauss and the force representation of this perturbing potential with Lagrange. And since we wrote the original perturbation as a potential, in this particular case, applying Lagrange's equations is way easier than going the force route. It depends a lot on how you set up the problem and what the source of the perturbation is. If the perturbation is naturally expressible directly as a force, then you're probably better off using Gauss. If the perturbation is more easily expressible as a potential, as in the case of the spherical harmonic expansion of the geopotential, then it's likely that applying Lagrange's equations will be simpler. But regardless of what you do, you will get the same result, and you can apply exactly the same averaging in both cases. Next, let us consider the rate of change of the argument of periapsis, omega. We will use Lagrange's equations this time. And remember that those told us that the time rate of change of the argument of periapsis will be a function of the partial of the perturbing potential with respect to the eccentricity and the partial of the perturbing potential with respect to the inclination. Here's once again our perturbing potential. It is an explicit function of I only via this phi term. And so we take the partial derivative, crunch through all the values, and we get omega dot is equal to 3 mu j2 times the equatorial radius of the body squared over the orbital radius cubed times the specific angular momentum magnitude times cosine squared of the inclination sine squared of the argument of latitude. We do exactly the same kind of averaging over one orbital period. We express d omega dt as d omega d theta times 1 over d theta dt, take the same kind of approximations that we previously did, and we get this expression. And this is known as apsidal rotation. Much like in the case of nodal regression, what we find is that we have a strict linear trend in omega when averaged over a full orbital period. Once again, you'll note that the sign of this is a function of the inclination. And so in cases where this term leads to a positive value, you will have a positive change in omega. And in cases where this evaluates to a negative value, you will have a negative change in omega. But regardless, you will have a linear trend over the course of many orbits of the argument of periapsis. And once again, in this figure, we've exaggerated the results slightly for clarity. This is now showing a polar orbit, so an exactly 90-degree inclination orbit at, again, 1,000 kilometers altitude and 0.1 eccentricity. And this is just showing 10 orbital periods, but the rotation rate has been exaggerated by a factor of 100. This delta omega shown here is what you would get over 1,000 orbital periods rather than just the 10 shown here. But it does behave exactly as indicated. And so this effect is just clocking your argument of periapsis continuously around and around the body. And remember, both these effects are happening at the same time. These are both due to just the oblateness of the central body, just this J2 term. So apsidal rotation and nodal regression and any other changes in the orbital elements are all happening simultaneously. But we can look at each one of them independently because we have these equations, either gas equations or Lagrange's planetary equations, which allow us to solve for their rates of change and then average those rates of change one at a time. A few more interesting things to note here. In the limit, as the inclination goes to 0, the derivative in theta of omega plus capital omega, averaged over one orbital period, goes to 3/2 J2 times the central body's equatorial radius over the orbital semi-parameter quantity squared. So for equatorial orbits, for orbits where we cannot distinguish between these two angles because the inclination, the central rotation of the Euler angle set is 0, the joint average effect is just a steady change in the summed angle that has a rate of 3/2 J2 times RB over L squared. The other thing to note is that for all other terms, their rates of change averaged over a full orbital period are 0. So to first order, and only accounting for the J2 effects of the geopotential of the central body, only the argument of periapsis and the longitude of the ascending node change. Remember, we can average the perturbing potential before applying Lagrange's planetary equations. So rather than doing the averaging after the fact, after we found the rates of change of various orbital elements, as we've done in the last two examples, let's see what happens if we average first before applying Lagrange's planetary equations or before going to a force expression. So once again, we are just considering the perturbation due to the J2 term of the geopotential expansion. We once again make the substitution for phi. It's equal to sine I sine theta. So here is our perturbing potential written in terms of the Keplerian elements. And we will define the secular potential as the average of this perturbing potential over the span of one orbit. And so once again, all we have to do is average over any of the fast variables. Fast variables are any of the angles that describe motion along our pure two-body orbit. So any of mean anomaly or eccentric anomaly or true anomaly or equivalently argument of latitude. And all of these over the course of one orbital period go between 0 and 2 pi. And as before, we don't really care where we're starting. And so without any loss of generality, we can take the limits of this integral to be 0 and 2 pi. So there are two parts of this expression that vary in time. There's the orbital radius, which appears in the denominator here as r cubed. And then there's the sine squared theta term. We can look at these independently of one another and then put them back together. First, let's look at the average of r to the negative third. This will be 1 over 2 pi times the integral from 0 to 2 pi in the mean anomaly of r to the negative third. We're going to change from an integral in mean anomaly to an integral in true anomaly, which has the same limits. And so we multiply this dm dt by dt d nu times d nu. You will recall that we've previously shown that nu dot is h over r squared, and so dt over d nu is r squared over h. And this allows us to simplify this integral to the integral from 0 to 2 pi of 1 plus e cosine nu over the semiparameter d nu, and this evaluates to a to the negative third times 1 minus e squared to the negative 3/2 power. And again, you should verify that you agree with this. For the second bit, we have this sine squared theta term, and it is still being scaled by r cubed. So we need to consider these jointly. And so we're looking at the average of r to the negative third times sine squared theta. We make the same change of variable to get this integral in d nu. And so we have the same r squared over h term here. And we're going to replace theta with its definition of omega plus nu, since we need to isolate the variable that we're integrating in. And so this integral can now be rewritten as n over 2 pi LH times the integral from 0 to 2 pi in nu of 1 plus e cosine nu sine squared omega plus nu. And this entire expression integrates to just pi, which again, you should convince yourself that this is true, which means that this entire term averages to 1/2 a to the negative third times 1 minus e squared to the negative 3/2. So putting this together, the secular perturbing potential due to J2, that is the orbital period averaged perturbing potential due to J2, is negative J2 mu r squared b over 2a cubed quantity 1 minus e squared to the 3/2 times quantity 3/2 sine squared I minus 1. So we can now go ahead and plug this expression into the relevant Lagrange planetary equation. Let's, for example, look at the rate of change of the longitude of the ascending node. This is the partial of the perturbing potential with respect to I times 1 over root mu a 1 minus e squared sine I. And for the secular perturbing potential due to J2, this whole thing evaluates to negative 3n times the equatorial radius of the central body squared times J2 over 2l squared cosine I. And you will notice that this is very close, but not exactly equal to the average expression that we've previously written. And it differs by just this one factor of n. So this secular omega dot is equal to the mean motion times the average rate of change of omega over one orbit. So once again, we show consistency in our results, regardless of whether we do the averaging before or after applying the perturbation equations. The only thing that happens is that we have this additional term of n, of the mean motion. And that makes sense because these things are telling us slightly different quantities. This is giving us a time rate of change everywhere on the orbit, while this is telling us the averaged rate of change over the full orbital period. And so you just multiply it by the mean motion of the orbit in order to convert between the two. In terms of what they're predicting for what the orbit is going to be doing in its in the evolution of its orbital elements, they're literally giving you exactly the same information. And as before, this term has no dependence in lowercase omega or capital omega or mean anomaly, and therefore the secular rates of change of the semi-major axis and the eccentricity and the inclination are all zero. And so once again, we have the result that to first order, counting only J2 perturbations, the only things that are affected are the argument of periapsis and the longitude of the ascending node.